Let us consider example 1, where we want to determine the voltages across the three resistors. In the circuit below, we have a current source that provides 4 amps to a network of resistors where R1 and R3 are in a series configuration, and their equivalent is in parallel with R2. R1 has a resistance of 1 ohm, R2 has a resistance of half an ohm, and R3 also has a resistance of half an ohm. To employ node voltage analysis, we are going to follow 4 steps. And the first step is to assign nodes, i.e. n number of nodes within our system, and leg currents to all branches and elements. In our circuit above, we have 3 nodes designated as A, B, and C. Node A exists between our current source and R1 and R2, B exists between R1 and R3, and C exists between our current source R2 and R3. We are going to designate node C as our ground. Additionally, we have to assign our leg currents. We'll do this in a logical manner. IS enters node A, where I1 can leave node A and head towards node B, and we have a unique branch current I3 going from node B to node C. I2 leaves node A and goes to node C. Step 2 is to assign voltage potentials consistent with our passive sign convention across our resistors. That is, V1 exists across R1 as indicated by the direction of I1, V3 exists across R3 as indicated by the direction of I3, and V2 exists across R2 as indicated by the direction of I2. Our third step is to construct n-1 KCL equations applied to our non-zero nodes. That is, we have 3 nodes within our system, thus we have to construct 2 KCL equations, and if we are going to neglect the ground node, we will apply our KCL equations to nodes A and B. Constructing our KCL equations, we'll start with node A. At node A, we have to recognize that we have 1 current entering and 2 currents exiting. That is, IS enters and I1 and I2 exit. Therefore, our KCL equation at node A is 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 equal to I1 plus I2. Next, we will construct our KCL equation at node B. At node B, we have 1 current entering and 1 current exiting. That is, we have I1 is equal to I3. The last step of our node voltage analysis procedure is to apply Ohm's law in terms of our node voltages. That is, for our KCL equation at node A, IS is entering with a numeric value of 4, and I1 can be expressed in terms of our node voltage, such that I1 is equal to VA minus VB per R1. I2 is expressed as VA less VC over R2. We recall we designated node C as our ground node, i.e. a 0 voltage potential. We can do the same for our KCL equation at node B. I1 is equal to VA minus VB per R1, and I3 would be VB minus VC per R3, where VC is ground, i.e. has a 0 voltage potential. We have 2 equations and 2 unknowns. IS is equal to 4 amps, R1 is equal to 1 ohm, R2 is equal to half an ohm, and R3 is equal to half an ohm. Solving our systems of equations, we find that VB is equal to 0.5 volts, and VA is equal to 1.5 volts.